Here the topic is Gauss Divergence theorem, which gives the relation between surface and volume integral. Here f vector is a if f vector is a vector point function having continuous first order derivatives in the region here the region is given by V bounded by a closed surface S bounded by a closed surface S. Then here the relation is double integral over S f dot n cap ds equal to triple integral over B divergent f dv. Here n cap is unit outward normal vector. Here the surface is the closed one and the region is given by V. So the LHS gives the surface integral and RHS gives the volume integral. Now we see the one problem based on this. Verify divergence theorem for f vector is given by x square minus yzi plus y square minus zxj plus z square minus xyk taken over the rectangular parallelopiped here x varies from 0 to a, y from 0 to b and z from 0 to c. Here the given surface is rectangular parallelopiped. Okay, first we write the statement of Gauss divergence theorem. What is the statement is triple integral over S f dot n cap ds equal to triple integral over V divergent f dv. Okay. So this is the rectangular parallelepiped. It is given in 3 dimensions. So first we do the RHS. RHS, for doing RHS, what we need means we need divergent f. What is the f vector they have given? X square minus yzi plus y square minus zxj plus z square minus xyk. See, I think we remember how to find divergent if f vector equal to f1i plus f2j plus f3k, then the divergent of f is dou by dou x of f1 plus dou by dou y of f2 plus dou by dou z of f3. So here f1 is this one and f2 is j component and F3 is k component. So, which is equal to dou by dou x of F1, that is x square minus yz plus dou by dou y of y1, y square minus zx plus dou by dou z of F3, that is z square minus xy. So, which is equal to dou by dou x of this one is 2x. Similarly, for the second term, when we do partial differentiation with respect to y square differentiation 2y. For the third term, when we differentiate partially with respect to z, we will get 2z. So, divergent f is 2 into x plus y plus z. So, for RHS, what is the formula? Triple integral divergent f dv. So, triple integral divergent f, now only we calculated, that is x plus y plus z. Okay, here we have to find out the limits. Here the limits they have given in the problem directly, that is x varies from 0 to a and y varies from 0 to b, z varies from 0 to c. So the order is dx, dy, dz. Okay, first we do the inner integration with respect to x, keeping y and z are constant. So write outer integration, middle integration as it is. Integration of first term is x squared by 2. Second term yx plus zx. Here the limit is 0 to a dy dz. Now the inner integration over, we have to apply the limit for x, because we did the integration with respect to x. So 2 times 0 to c, 0 to b. Here a square by 2 plus ay plus az dy dz. So inner integration is over. Next we do the integration with respect to the next variable, that is y. So here we keep the next variable z as a constant. So which is equal to 2 times 0 to b. First term is a square by 2, which is the constant. So the integration a square by 2 y plus a. Here y integration y square by 2. Third term is a z. So the integration is a z y. The limit is 0 to b dz. Now apply the limit. Here we apply the limit for the variable y. So 2 times 0 to c a square by 2b plus a b square by 2 plus a z b. Now the inner integration over, middle integration over. Lastly, we do for the outer integration with respect to the variable z. See the function. Here the function has only the variable z. So 2 times first term integration a square b by 2 z plus second term a b square by 2 z plus ab is the constant, z integration z square by 2. Here the limit is 0 to c. So apply the limit for the variable z. So all the two get cancelled. The first term is a square bc, a b square c plus ab c square. Now we can simplify by taking common, taking abc outside. We will get a plus b plus c, which is our RHS. So RHS portion is over. Next we do for the LHS. So for LHS also we need the same answer, this answer. What is the LHS? LHS is nothing but surface integral, double integral f dot n cap ds. So to evaluate the surface integral, we have to divide our surface into 6 surfaces. Okay. So in the rectangular parallelepiped, here x, y, z. PO. So in the rectangular parallelepiped, we know it has 6 faces. So we have to divide it into 6 surfaces. X1 plus S2 to 6. So here we have to find for each surface what is the equation of each surface and what is the unit outward normal vector. This portion is a very important one. We have to find n cap for each surface and also we need to find ds. All these are very important ones. So we need this data. So first column we are taking surface and the second column equation and n cap. What is the value of n cap? And the third column ds. Here, what is the xy plane? So here the xy plane is OABC. So OABC. Okay, it is a xy plane. In the xy plane, we know which variable is 0. In the xy plane, z is 0. So z equal to 0. And what is the value of n cap is, see here the unit outer normal vector is I cap means the opposite side, the unit normal vector is minus I. Similarly, in the y direction, it is j means the opposite side, it is minus j. Here k means the opposite side minus k. So for OABC in the xy plane surface, the unit outward normal vector is minus k. And z equal to 0 means we know dz is 0. So dz is 0 means ds is, it has only dx dy. So this is the first surface. Second surface, parallel to xy plane. Which plane is parallel to xy? This one, EDGF. EDGF. DGF. Parallel to xy plane. So for parallel to xy plane, what is the equation means? The other variable should be constant. Here the other variable is z. Okay, so Z is constant. Here they have given Z varies from 0 to C. So we have to write Z equal to C. And dz is 0 because differentiation of C is 0. And n cap is for this plane EDGF, the unit outward normal vector is K vector. So n cap is K vector and ds is same one, dx dy. This is for xy plane and parallel to xy plane. Next, we go to YZ plane. So here, which one is YZ plane? This one, OCGF. OCGF. YZ plane. In the YZ plane, we know which variable is 0, x equal to 0, so dx equal to 0. Here, what is the unit outward normal vector for x? O, C, G, F. Here the unit outward normal vector is minus I. So n cap is minus I. And ds is, dx is 0 means ds is dy dz. The fourth surface is, what is the fourth surface? Parallel to YZ plane. So parallel to YZ plane, which plane is parallel to YZ plane means ABDE. Okay. Here See here A, B, D, E. Here the unit outward normal vector is I. Unit outward normal vector is I. So parallel to YZ plane is which one? Parallel to YZ plane is A, B, D, E. A, B, E. Here unit outward normal vector is what we said, that is I vector. And here what is the equation is the other variable. YZ plane, what is the other variable? X. X is constant. Here the constant they have given x equal to D. So dx equal to differentiation of constant is 0 and ds is dy dz. So xy over yz over. Next we go to zx. Zx plane. So which plane is zx? In zx plane, OAEF. OAEF. Here the unit outward normal vector is minus j. AEF. N cap is minus j. So in the Z explain, the what is the equation is y equal to 0, dy equal to 0, and ds is dx dy. The last surface is parallel to Z explain. So which one is parallel to Z explain? So this is Zx. Parallel to Z explain is BCGD. BCGD. For this, the unit outward normal vector is J. BCGD. Here the equation is y is constant. So y equal to b, dy equal to 0, n cap is j, and ds is dx dy. So these are the conditions we are having for the each surface. So now we are going to evaluate the integral of each surface. Okay. The first surface. Over the surface S1. So S1 means this is our S1. So in XY plane what they have given. So okay, first we can write what is our F dot n cap. So double integral over S F dot n cap ds equal to double integral over S. What is F vector they have given? F vector is x square minus y z I plus y square minus zx j plus z square minus xyk dot n vector n cap. Okay. So for the surface S1, what is the value of n cap? N cap is minus k. N cap is minus k means we are getting only the k component with minus sign. So we will get minus integral z square minus xy. And ds is, what is ds? Dx dy. Okay. But in the surface, over the surface S1, what we said, z equal to 0. Okay. So z equal to 0 means this z is 0. We have to substitute z value is 0. So minus into minus plus xy dx dy. Here the integration is for x 0 to a and for y 0 to b. Now we have to do the integration. First integration with respect to x. Write outer integration as it is. Inner integration x square by 2 y 0 to a dy. So which is equal to 0 to b. Apply the limit for x. So a square by 2 y dy. Now we do for the outer integration with respect to y. Taking a square by 2 outside means y integration y square by 2. So the first surface value is a square b square by 4. Next, for the surface S2. So for the surface S2 means what is that? Z equal to constant, dz equal to 0, n cap is k vector. So these are the condition we see. So integral over S2 equal to integral over n cap is k vector means again we will get only the k component. Because if you are substituting n cap is k vector, we know k dot k is 1. I dot k is 0, j dot k is 0. So we are getting only the k component z square minus xy. And dz0 means dx dy. But here we are having z equal to c. So substitute z value is c here. C square minus x by dx dy. And x limit is 0 to a and y limit is 0 to b. Now, when we do the integration, first do the integration with respect to x. So, write outer integral as it is c square x minus x square y by 2, 0 to a dy. Now, apply the limit for the variable x. Upper limit is a. So, when we apply the upper limit, what you will get? ac square minus a square b by 2 dy. A square y by 2. Okay, y by 2 dy. Now the inner integration over. Now we have to do the integration with respect to y. So this is the variable y. A c square y minus a square by 2 y integration y square by 2. So 0 to b. So what we will get? ABC square minus a square b square by 2. Okay. This is for the second surface. For the third surface. For the third surface, what is the condition? We said x equal to 0 and dx equal to 0. N cap is minus I. Minus I means we will get only the I component. What is the I component? This is the I component with minus sign. So, double integral over S3 is equal to, we will get only the I component. What is the I component? X square minus yz. Dx is 0 means here we will get dy dz. And what is the y limit? 0 to b. Z limit 0 to c. But very important one is we have to substitute the value of z. X equal to 0. Here we have to substitute x equal to 0 here. So x equal to 0 means we will get only yz minus into minus plus. So we know the integration. When we do the integration, the answer is b square c square upon 4. Next, for the surface S4. So S4, what is the equation? X equal to constant. That is x equal to a, dx equal to 0, and n cap is I, and ds is dy dz. Okay. Here also we will get only the I component. So what is the I component? That is x square minus yz. ds is dy dz. Y limit is 0 to b and z limit is 0 to c. And also what is the important one? We substitute the value of x here. What is the value of x in this surface? A. So x equal to a. 0 to c, 0 to b, a square yz dy dz. So when we do the integration, what is the answer is a square bc minus b square c square upon 4. Next, we move to the next surface, Fy. The Fy is for the fifth surface. What is the equation? Y equal to 0, dy equal to 0, and n cap is minus j. And ds is dx dz. So double integral over Fy f dot n cap ds equal to, here n cap is minus j means we will get only the jth component of f vector. What is the jth component? This is the jth component, y square minus zx with negative sign. Why we have negative sign? N cap is minus j. So minus y square minus zx dx dz. And the x limit is 0 to a, z limit is 0 to c. We have to substitute the value of y equal to 0. So 0 to c, 0 to a, zx, dx, dz. When we apply the limit, we will get a square c square upon 4. For the last surface, S6. X's equation is y is constant. Here they have given y varies from 0 to b. So y equal to b, dy equal to 0, and n cap is j vector. And ds is dx dy. So double integration over S6 equal to, we will get only the j component, that is y square minus zx dx dy. X limit is 0 to a and y limit is 0 to b. Here again substitute the value of y. So y value is in the surface y equal to b. So 0 to, sorry, here dy is 0. So ds is dx dz. So this is dx dz and it is 0 to a, 0 to c. So 0 to c, 0 to a, substitute y value. So that is b square minus zx dx dz. So when we do the integration, what is the answer is a b square c minus a square c square upon 4. See, lastly, we have to add all the integral. Therefore, f dot n cap ds. What is the first integral? Value a square b square by 4. Second integral abc square minus a square b square by 4. Third integral b square c square upon 4. Fourth integral a square bc minus b square c square upon 4. Fifth integral a square c square by 4 plus, so these are the integral answer we got. Isn't it? This is the first integral value and this is the second integral value and third integral value, fourth integral value, fifth integral value, and this is the last one. So when we add all these, what will happen? These all the terms get cancelled. So we will get ABC square plus a square BC plus ABC square plus a square BC plus a, here this AB square. See here it is AB square C. AB square C. So when we take common, what we will get? A plus B plus C, which is our LHS. Therefore, LHS equal to RHS. Hence, the Green's theorem is very. Hence, the Gauss divergence theorem is verified.